record on this computer. So we're starting in Unit 1, obvi, describing and displaying data. All right. So, funny cartoon aside, it gets the idea because like we're talking about two normal distributions, whatever those are, and then one that's the, he's not the normal curve. It's because it's a different sort of shape, right? So that's kind of what we're going to be working towards. We're going to be discussing measures of central tendency, but then we're going to be using that in order to make or draw a conclusion about, oh, it's already starting, about the nature of a distribution. Distribution being just a listing of data, right? So we have mean, median, mode, range, and mid-range. So that's where we start the journey. Now, range isn't actually a measure of central tendency, but it kind of doesn't make sense to talk about mid-range without talking about range first, right? So we have our notation, that funky looking E looking thing, that's Greek letter sigma, capital sigma. That sigma notation, it represents sum, right? The X is an individual data value, and the N represents the number of values in the set. So I'm going to show you a formula that's going to just seem to make the concept of a mean sound way more complicated than it needs to be, but I want you to be comfortable with the notation so that if you ever come across that, you know what you're looking at. But when you find the mean, you're just gonna use the skills, the computational skills that I show you. So we're looking at the notation for a mean. So I'm gonna note that over here. It's X bar. All right, it's called X bar. It's weird. Couldn't have thought of some more creative name for that. But X bar is equal to the sum of all the X values divided by the number of values in the set. All right. So, there's more elaborate notation, but I figure this is elaborate enough. So this, whether you call it by its true name, X bar, or X with a line over it, however you want to call it, it stands for we call a sample mean. There's two types of means. One of them is a sample mean and the other is known as the population mean. And there's different circumstances in which you would use each one. All right, so we'll discuss that as we go further, but for now we're only focusing on samples. And really, if you kind of look at the course, it's got three parts. The first part is really all about samples. The second part is all about populations, and the third part just kind of brings it all together. So you really don't have to worry about the population stuff until the second unit, right? So this part here means the sum of all the X values. But if you want to write it in simpler terms, you might say add up all the X values. All right, so we're adding up the X values. Keyword there, add. That last little bit, that N, is count up all the X values. So the keyword there is count. All right, one of them you're taking a sum, and the others you're just simply pointing and saying 1, 2, 3, 4, however many there are. Right, so that's part of the fun. And so the notation, yeah, what does it add to the situation? Oh, so this is the same as averaging. Yeah, you just add them up and divide. Oh, okay, I knew that. What's up with all this notation? Again, it's just to develop a little more comfort, a little bit more fluency. All right, but ultimately we're just adding these bad boys together and dividing by the total number of values in the set, which is 6, I believe. I'm going to chuck in the notation here, though. X bar is equal to, and then we just add them up and divide by 6. All right. We're not overly concerned with rounding at this point, but I have a whole presentation related to rounding coming down the line. At this juncture, we're just going to focus on the skill, the operation of finding the mean, right? So it's up to you what kind of device you want to use in order for you to do your calculations. You can use the Desmos calculator. You can use a calculator on your phone, calculator on a computer. It doesn't make a difference to me, right? So, you know, down the line, we'll see that there are certain skills where it's like, wow, I have to do this using some other kind of technology. We'll cross that bridge when we get to it. All right. So what I'm going to do is I'm going to pull up my calculator here and hope that it actually shows up. Well, it would have been nice. It looks great on my screen, but it's just it's a simple calculator. So I'm just going to do a quick sum here. So 15.1 plus 17.5 plus 18.3 plus 14.1 plus 3.2 and a 6. So 74.2 on top and 6 on the bottom. All right, that number sounds familiar from the last like 40 times I taught this class, but it could still be wrong. So I'm just going to do a quick double check. Looks reasonably okay. I'm going to take that 74 by 0.2 and divide by 6. And we're looking at 12. It's got a repeating decimal, so I could say 12.36 repeated. All right, so I didn't really have to talk about rounding because it didn't end up being overly relevant. I mean, I suppose I could have rounded it, but it's also a repeating decimal, so I could just note it this way. All right, so that part should be okay because it's not your first time, and you know, like, okay, so I know you for a week. Who are you to say? You've definitely seen averaging before. You know, that's not a new one. Some of the other stuff, okay, yeah, you'll see some interesting things that I haven't seen that before. But this is one of those things where you've definitely seen it before. All right, so something just crapped out. Median's middle value of the data set with the numbers in ascending order. So you have your steps. Well, you got there's a couple ways you can handle something like this. Let me pause the video real quick. The short answer to that is it depends. You know, so you have the freedom to represent your answer any way you want. If you decide to round and you weren't told to round, you just got to make sure you round correctly. So if you decide to round this to the nearest tenth and you put anything other than 12.4, then, yeah, well, it's incorrect based on the decision that you made to round to the nearest tenth. Right? If you go to the nearest hundredth and you round it to 12.37, that's perfectly fine because that would be correct. Right? Now, if the direction said specifically to round it in one way or another, then I think that's obvious because you're just following directions. Right? So when there are no rounding instructions given, my policy, and we'll talk about like under what circumstances it's really mathematically appropriate to round and under what circumstances it's not. But my policy is if you're not given rounding instructions, you can round as long as it's only in the last step of the problem. You never round as part of the process. It's never like an intermediate step. It's got to be the final step, and you round appropriately based on what your decision was. Right? So hopefully that helps a little bit. The median, I put a process here. I put the most popular process for finding the median, but there are other ways to do it. The most popular way is you just put all the values in increasing order, and then you just count to the middle. If there's two values in the middle, then you find their average, right? So, like in the case of in A, where the smallest value is 1, then we have 2, 3, 4, looks like 6, 8, 9, 14, and 24. All right. And so when I'm counting to the middle, is one of the things that's kind of tricky to show over a device. So I'm going to use tick marks to show that I'm counting off from each side. So I'm counting inward. So the one, it's kind of like a cancellation technique. The 1 and the 24 cancel each other out. The 2 and the 14 cancel each other out. I'm working my way counting to the middle. The 3 and the 9, the 4 and the 8, and that's going to leave me with the 6. All right, so that would be my median. All right, as far as notation is concerned, unless I miss something along the way, the notation for median is just MED. All right, so we would say median is equal to 6. All right. Another way to handle it would be to cancel by size. Without putting it in order, what you can do is you could say, all right, well, wait a minute. I have, and I'll just rewrite the numbers here in their original form. And it's 6, 8, 4, 3, 1, 2, 9, 14, and 24. So another way I could handle it would be to say, all right, let's, without putting in increasing order or decreasing order, it doesn't matter. What I could do is I could say, all right, what's the smallest number? 1. What's the largest number? 24. So cancel the 1 with 24. Out of what remains, what's the smallest number? 2. What's the largest remaining number? 14. So cancel the 2 with the 14. What's the smallest remaining number? 3. What's the largest remaining number? 9. So cancel the 3 with the 9. Smallest remaining number? 4. Largest remaining number? 8. Cancel the 4 with the 8, and you'll be left with a 6 that way. All right? It doesn't matter to me which way you do it. Bottom line is, I mean, I'm going to end up showing you how to do this on using technology down the line anyway. So it's up to you, but I find the second way that I did it to be a little bit easier, because you're essentially doing the same stuff you did when I did it the first way, except you're not wasting your time writing it in increasing order. All right? For B, I'll just stick with the process that's written there. Rewriting it, it's a small data set anyway, so it's not that big of a deal. We have 0, 1, looks like we have a couple of 2s, 3, 4, 5, and 6. All right, so it's just, again, counting to the middle. So I'm going to take my 0 and wipe it out with the 6. The 1 with the 5, one of the 2s with the 4, but then I can't cancel the 2 with the 3 without being left with nothing. So what we're getting at is the idea that the median has to be in between 2 and 3. So instead of just kind of like selecting at random and saying, okay, I choose 2.1, that's in between 2 and 3, what we do is we find the average, right? So the median here is going to be 2 plus 3 over 2, which is 5/2, which is 2.5, which is directly between 2 and 3. So once you realize that it's, okay, so the median is talking about if there's two numbers, it's the one that's directly in the middle. Now you get the idea. And so you would say, okay, well, I just got to figure out what that is. So if the two numbers are 5 and 7, then I would say, okay, well, what's in between 5 and 7? So 6, and there you go. All right. So let me pause for a second. Resume recording. Yeah, so the question was, if you have 2 values remaining over after this process, are you always going to be taking the average? And the answer is yes. All right, so you're always going to be finding the average of whatever those 2 values are. And really, you could think about it as like, all right, even with the 1 value, you would just be taking the average of that, like in part A, you would be taking the average of 6 and itself, which would still be 6. Right? But in the case of 2 numbers, you actually have to perform the operation. So the modes, I would say it's the easiest one. Most people, I think, would agree, but it also has a couple of moving parts, so you just got to be careful. If you know the rules of the game, it's all fine. Okay, so the mode is the most frequent value. As long as you know that you can have more than one, and you could also have no mode, then that usually gets you where you need to go. So to the best of my knowledge, I've been doing this a while, so I think my knowledge is, I don't want to say complete, but it's substantial. We have no notation for mode other than to say mode. All right, so the mode here is the number that occurs most frequently. So in this case, that appears to be the number 7. 7 occurs more than everything else. All right, so 7 is not the mode because it repeats, just because it simply repeats. It occurs more frequently than everything else. That's why it's the mode. So that's the justification for why there's no mode in the second example, because there is no number that occurs more frequently than any other number. Everything occurs the same number of times. In C, the 1 occurs twice. But the 3 also occurs twice. So 1 doesn't occur any more frequently than 3, and vice versa, but they both occur more frequently than 7, 8, or 9. So I could say that 1 and 3 are the mode in part C. But then this is my version of a trick question in D. And this is what I was saying here. Just because a value repeats doesn't mean that it's necessarily going to be the mode. Like 1 and 2 both repeat, but they don't repeat as frequently as 3 does. So 3 occurs more frequently than everything else. So 3 is my mode in this case. All right. So, it's, like I said, it's not complicated. It's just, there's a couple of moving parts there. So as long as you have a sense of what those moving parts are, you're fine. All right. For range and mid-range, the difference of subtraction between the highest and lowest values, mid-range is the tricky one. I used to have this spiel that I would share with people during in-person instruction, and that is, and my percentage always went down every year, but I would start off with like 50% of people in this class are going to get the mid-range question wrong on the first unit test. And then the next semester, I would say 40%, then 20%, then 10%. And then eventually it got down to like 2% because I kept emphasizing the point that there's something weird going on with the mid-range. All right, so I'll get to that in a second, but I just wanted to kind of alert you to the fact that there's a little funny business with the mid-range. So let's start off with the range, which is just simply the highest value minus the lowest value. So the range is 16, and all it's talking about is the displacement or the distance between the lowest and the highest value. So how many steps does it take to get from the lowest to the highest value? So that's the range, all right? But when it comes to mid-range, it's the average of the highest and lowest values. So the mid-range so 1 plus 17 or 17 plus 1, it doesn't matter, divided by 2. So that's 18 divided by 2, which is going to be 9. All right, the reason why this is a common misconception is because people who, and I don't want to say that they're not studying, except to say that they probably didn't study this particular topic. Maybe they studied everything else. They figure, mid-range is probably okay. I don't need to worry about that. I know what the range is, and this is mid-range. So I'll just take whatever my range is and divide it by 2. So you get 8, but that's incorrect because the mid-range is the average of the highest and lowest values, right? Or lowest and highest. So that's the one thing you got to be careful about. And I always put a question related to the mid-range on the unit test, and the final exam. So I would star that one, underline it, do whatever you got to do to draw your attention to it. Maybe even send yourself, I've been actively encouraging this one, send yourself a little note for, I think it's October 7th, whatever I put in the syllabus. I'm pretty sure it's October 7th for that first unit test. Just put it in your calendar, like on your phone or on your computer, and just have it send you an alert saying, review mid-range. sometime during that day, so that you're not one of the unprepared people when it comes time to take that test. Just something to think about. That's kind of where I got to in life, where it's like everything either ends up in a calendar or it's marked unread as an email, just because if I don't do it that way, I lose track of things and life falls apart. Right. Next page, we have easily the most intimidating formula that you've ever seen in your entire life. That's true for some of you, maybe not so much for others. It depends. I don't know, like if you've taken some crazy science class, you've seen some pretty intimidating formulas, but yeah, as for math, it's like, whoa, this is a doozy. LQ minus 1.5 IQR, UQ plus 1.5 IQR. It's like, are those variables? Is that notation? Like, what the hell is this? So obviously we need to talk about these terms. LQ, I'm going to make a note of this. LQ stands for lower quartile. All right. So that's wonderful. There's a name that goes along with the abbreviation, but it doesn't do us much good if we don't know what that in and of itself means. So lower quartile is also known as the 25th percentile. So I'll make a note here, 25th percentile. And we're going to have to talk about percentiles at some point, because you see percent as part of the term percentile, and you're like, well, I think I know what it means, but it doesn't always end up being the case. So the lower quartile is the quarter-way point from the lowest to highest value. So it's the quarter-way point from the lowest to highest value. And that's information. What we do with that information is going to be the key ingredient. Now, if you start thinking in terms of fractions, you're like, okay, well, we know how to find the halfway point. We did that on the previous page. That's the median. Well, isn't the half a quarter? So if I find the median, break the data up into two separate halves. I got the lower half and I got the upper half. I just find the median again. I'll walk you through that in a sec, but that's the gist of it. We know what the median is. We do need to know what the UQ stands for, which is upper quartile. And that is the 3/4 way point. All right, and this is not going to make me too many friends. But it might be incentive to get some annotation software if you don't already have any. I am going to make it a priority. I'm going to change this to 75th percentile in a sec, but I'm going to make it a priority to come up with a nice list of really what I think are really good apps, ranging from free to paid apps that you can make use of, because I have an unfair advantage here. Copy paste. Whoever invented that is the hero that we need right now. All right. So there's one other quote unquote variable within that nasty formula, and that is the IQR. That's the interquartile range. That's not a particular location within the data set, but instead it's actually the difference between two values. It's the difference between the upper quartile and the lower quartile. So it's UQ minus LQ. So it is the distance from your lower quartile to your upper quartile. All right. And distance implies difference. All right. Whenever you're finding the distance between two objects, you have some sort of reference point. You're finding the difference between the location of those two objects based off of that reference point. All right. So, how do I find the distance between two cars? Well, I got to know how far they are away from me. I'm a third party, so the first car is 20 feet away, the other car is like 100 feet away. So those two distances subtracted give me the distance between them. All right. So we need a few things. We need that formula, but we also need kind of like a little bit of a understanding of what those brackets are going to represent. But I'll get to that in a second. So first, in order to find the lower and upper quartiles, we're going to need to find the median. All right, so that's where I'm going to start. So same as we did before, except I'm not going to cross out the numbers, right? Because it's going to get a little too crazy. Maybe I'll use a highlighter. So lower, I'll get a bigger highlighter. Lowest with highest, it's already in order, so that's good news. Lowest remaining with highest remaining, lowest remaining with highest remaining, lowest remaining with highest remaining. Right? So this entry here is my median. All right. So what I'm going to do is I'm going to focus on the values that are less than that median. All right. So the 2, 4, 5, and 6. That's my set of data. That's the lower half of data. Which, understandably, hopefully, would make this the upper half. All right, so looking at these, kind of as if they're their own separate problems. You would say, okay, well, I have this data set consisting of 2, 4, 5, and 6. What's the median of that data set? Okay, so my lowest value in this data set is 2, corresponding with the highest value of 6. I can't go too far before I'm left with 2 values in the middle. All right, so I'm looking at 4 and 5 making up the median of the lower half of data. So halfway between those two values is going to be my lower quartile, which is 4.5. Again, we get that by finding the average of those two numbers. But again, if you know that it's going to be directly in between, the median is going to be directly in between two numbers. What's between 4 and 5? 4.5. Same idea on the other side. We know as we're working our way in, 8 is the lowest value. So we're disregarding the median itself. 8 is the lowest value, 42 is the highest value. We're working our way in, 8 cancels out with the 42. We're left with the 9 and 10. So now I'm looking at these two comprising my upper quartile, which would be 9.5. All right, so my lower quartile, 4.5. My upper quartile, 9.5. The IQR is the difference between the two, so 9.5 minus 4.5. That's going to be equal to 5, clean 5. So we have all the ingredients for our formula now. Now we just got to actually pop it all into the formula. It's sometimes easier said than done. So I'm going to reproduce that formula down here. I'll handwrite it though. So we're looking at LQ minus 1.5 times the IQR. I'll write the multiplication symbol there. Comma. So a formula that actually involves a comma. That's kind of weird. UQ plus 1.5 times the IQR. Right, so the LQ, 4.5, minus 1.5 times the IQR, which is 5. The UQ, 9.5, plus 1.5, that 1.5 is built into the formula, times the IQR. IQR again is 5. So it's the same IQR. All right. The brackets, the comma, they're all going to stay put. Right? Because what we're going to end up with here is an interval of values. And I'll explain what that interval represents in a minute. All right. But 4.5, we need the product of 1.5 and 5. So that's 1.5 on top of 5, multiply by 5. So 5 plus 2.5 is 7.5. So 7.5. And 9.5 also plus 7.5. So 4.5 minus 7.5 is negative 3. 9.5 plus 7.5 is going to be 17. All right, so this is an answer. We do have to interpret what the heck this answer means, because otherwise we're kind of spinning our wheels here. All right, it defeats the purpose completely. All right, so what we're looking at here is known as the interval of non-outliers. So I'm going to write that down. The interval of non-outliers. All right, and I'm going to take a second here. I know I'm zooming out significantly, but what I want to do is I want to bring this data set down real quick, reproduce it. I'm going to fix all this in a second. Actually, let me bring that in. You do all this the Zoom stuff in a history class. I'm sure they just leave up the same slide for the whole. Well, maybe not the same slide, but they don't have to scroll back all over the place and all that good stuff. Actually, I got to put this back first. There it is. Everything is like all PowerPoints, but this is a different story. All part of the fun, I guess. So this interval of non-outliers, we need to know what it's going to tell us. And like we didn't do much computation here. It just seems like we did. Right? The note taking, and again, if you're just watching it, you didn't even do that. But the actions, the addition, subtraction, operations, that not very significant, right? Not something that is beyond the ability of a simple calculator, right? It's the interpretation that's going to matter more than anything in this class. And you'll see that, and I mentioned this last time, that we're going to have many, many instances where the computation is super easy, barely an inconvenience, but the interpretation is what kind of drives everything, right? So what we have here is an interval of values that are not considered outliers, right, mathematically. So if the number falls between these two numbers, it is not an outlier, right? So I'm going to make a note of that. So if the given number falls between -3 and 17, it is not an outlier. Now, in math, oftentimes, the term that you're working with doesn't really define itself. There's just so many options. But like if you're familiar with calculus, you might hear of continuity, and it really doesn't mean what you think it means. And you can just take that as an example, even if you don't know anything about calculus. But I'm sure you could, if you thought long enough about it, you can think of even in another class where it's like, oh, the word makes you think one thing, but it really means something else. And we just did an example of that. That was the case of the mid-range. I thought it meant this, it meant that. This is one of the words that means exactly what you think it means. It lies out of what? Outside of something, right? It's just a matter of determining what is the meaning of that. And so that's where one of our big challenges is going to come into play, but we can work on that together. I'm going to pause the recording, check the chat, because I see there's been a big influx. So I'm going to look at the data set and just ask myself, yay or nay, do these values fall in between -3 and 17? Inclusive, that's what the bracket means. So if it's exactly -3 and exactly 17, then it's still considered to be in between the two. All right. So if I had a number line with a -3 and 17, and like I can make that happen. Just kind of, oh, maybe I can make it happen. I'm gonna move the image down. I can draw a number line, put some arrows on it. Here's -3, -2, -1, 0, and then I'll just kind of go by, let's say 5, 10, 15, and I'll throw the 17 over here. So sort of a modified number line, just to have a little bit of a visual. I mean, my artwork notwithstanding, okay, so it's a stretch to call that art, I know. But I could look at that 2 and say, okay, where does that 2 fall? The 2 would be somewhere over here. All right, so that's in the interval, because we need whatever the number is that we're testing. Everything's a test in this class, not like a unit test, but like a test of truth. Is it correct or is it incorrect? It's what we call either binary or binomial, depending on the day of the week. So you have, this is my lower bound, and this is my upper bound. All right, so the 2 falls in that interval, so that is out. It's not an outlier. All right, because it's an inlier. This is the interval that we're working with. If it's inside of that interval, then we're where we want to be. It's not an extraordinarily unusual value to the point where it shouldn't be there. That's what an outlier is talking about. If I say that a number is an outlier, I'm saying it's so absurd that it shouldn't even be there. Now, I give you that little bit of context, and you might say, oh, I know what it is. I didn't need to do any of your math. I understand. Right? So the 4 would be about right here. That's in the interval, so it's not an outlier. The 5, same deal. You have to show all this work? Of course not. Right? This is just for instructional purposes, but you can decide if this is a technique that helps you understand it, and diagramming it out like this is helpful, then by all means. 6, still in the interval. 7, 8, 9, boom, 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 all in the interval. 10, in the interval, so it's not an outlier. But 42, I can't even plot 42. I didn't make my number line long enough. So I'm looking at something. That 42 is way out of bounds. So therefore, and I don't try to go too crazy with the notation, but there's some things where it's just like, why wouldn't I use that? If you don't know this, 3 dots in the form of a triangle means therefore. You don't have to use that notation if you don't want. I just use it because I don't want to write so or therefore or in conclusion. 3 dots gets the job done. Up to you. Take it or leave it. It's your call. But therefore, 42 is an outlier. Right, so that's mathematically an outlier. And so as we move forward through the course, we're going to have to come to grips with the fact that sometimes something is one way mathematically, but in a practical sense, it's not necessarily true. Right, so I'm saying that this number is an outlier because I'm looking at all of these calculations. Look at these calculations, and 42 it doesn't satisfy those calculations. All right, so we got that. But now if I throw a little context to the problem and I say, these are the ages of students in an elementary school selected at random. Okay, the 2 is probably a little on the low side for that, but just kind of play along. All right, so if I say that these are the ages of elementary school students, then you look at it and say, I'm not doing the calculations, 42 is an outlier. Because if there's a 42-year-old Billy Madison notwithstanding, if there's a 42-year-old in an elementary school classroom, that's either a mistake or something weird's happening. Now, if I tell you that these are a random sample of the ages of individuals in an elementary school, period. People in an elementary school, not students. So anyone. Now you're incorporating adults. Mathematically, it says 42 is an outlier, but there's nothing wrong with 42 being part of this data set. 42 is perfectly liable to be there just like every other value, right? Because if I randomly select a person in a school, I could get faculty, staff, I could get students, so I can get a wide variety of individuals. And actually, the 2 might make sense because maybe I randomly selected people in an elementary school at a given time. Maybe it was after school and somebody was picking up their kid and they brought their toddler with them. So it's possible that all these numbers are valid and they should all be considered. Right? So you don't want to let the mathematics, and this is weird. You got to come to grips with this. In a stat class, we go this route and we say, you don't want to let the mathematics override the practical nature of the situation, right? So we don't want to let the calculation determine the truth when common sense is the overriding factor, right? So yeah, 42 shouldn't be here by the math, but depending on the circumstances, it might be perfectly okay, right? And that's something that we need to always be conscious of. When we start looking at statistical graphs, we're gonna take it as kind of like I was gonna say, sort of take it as a fact that testing for outliers is going to be kind of the way of things. We're always going to look for outliers, but we're not always going to remove outliers from a data set because there's not always a reason to. All right. Now, mean, median, mode of a frequency table. Different story altogether, way less complicated, but also kind of like, I mean, there's a learning curve to everything because you look at that formula and you say way less complicated, because it's like that's a nasty looking formula. It's way different from what we were working with before. I thought you said the mean was just add them up and divide. Yeah, but this is a different context, different circumstance. The mean here is related to a frequency table. All right, so that frequency table is allowing for, I always like to do this for at least one problem because it's definitely worth taking the time just to get the concept across. When we say that we're taking the mean of a frequency table, first we talk about the idea of frequency. The word frequency is talking about how often a value occurs. So in this case, it's how often the X value occurs. Hopefully I spelled occurs right. It's one of those words where it always just looks a little bit off. Like likelihood. I always feel like I screwed that one up. So anyway, what this means is that 1 occurs 10 times, 2 occurs 3 times, 3 occurs 1 time, 4 occurs 8 times, 5 occurs 5 times. So there's 2 ways to handle this. One, obviously a little bit more tedious. We could list out the number 1 10 times. So I could actually just say, take the 1 and write it 10 times. Take the 2, write it 3 times. Take the 3, only write it once. The 4 goes 8 times, and the 5 goes 5 times. Add them all up and divide by however many numbers there are. Or we could apply a little bit of a shortcut to help us get there without doing a lot of that stuff. So I'm gonna show you the shortcut, but I'm also gonna show you what that would look like if you were to expand it all out. All right, so the first step in the process would be to take your x values, each of them, and multiply them by the corresponding value of that. All right, so you're going across the rows. Each x gets multiplied by each f. So 1 by 10 is going to give me 10. 2 by 3 is going to give me 6. 3 by 1 is 3. 4 by 8 is 32. And 5 by 5 is 25. All right. So what this would be, and you don't have to, I mean, I don't know who's writing what, but if you are writing, you don't have to write this part. That number 1 occurred 10 times. So this is the same as 1 plus 1 plus 1 plus 1 plus 1 plus. I lost track. So I got 5 of them. 6, 7, 8, 9, 10. All right. So that's what this first entry would be. The next one would be 2 plus 2 plus 2. Then we would just have a 3. Then we would have 4 plus 4 plus 4 plus 4 plus another 4 plus another 4, and I think one more 4, but let me just double check. Yeah, feels right. And then 5 of those 5s added together. And this is like right on the very edge of what I'm willing to tolerate as just like a living human being, where it's like, if there's any more data points, I couldn't write anything like that. You know, like let's say 1 occurred 75 times. I'm not writing 1 out 75 times, but we can multiply 1 by 75. That wouldn't be bad, right? So that's the rationale here, because you'll still get the same values here. You'll still get the 10. You'll still get the 6. 3 is 3. That wasn't a concern. 32 and 25. But it's definitely like New York to New Jersey via London, you know, like we're definitely taking the scenic route. So if I want to find the actual mean, and I kind of jumped the shark here. I don't even know if that phrase makes sense here, but the table below is where all this work, I guess, should go. But the next step in the process would be to add all this stuff up, right? So I guess I could just pop it into the table down here so it looks a little nicer, aka the way I intended. All right, but that numerator is telling us to add up the values in the X by F column. And the other one should be a little bit more obvious based on this, because it's got the same kind of naming convention. You're adding up the values in the F column. And we have these two columns just kind of ready to rock and roll for us. So these two columns get added together. I'm sorry, added. Like you can do it together as in like simultaneously. So 10 plus 3 plus 1, so it's 14, plus 8 is 22, plus 5 is 27. And then 10 plus 6 is 16, plus 9, 19, plus 32 is going to be 51, I think. So 76. And so the mean, X bar, is just going to be the 76 divided by the 27. All right. So we got to crank out a quick calculation here. 76 divided by 27. And we're still looking at a repeating decimal. So this is good news because rounding, not everybody's as comfortable with it as everyone else. So it does take a little time to review, especially rounding rules specific to statistics, because there's significant digits and stuff like that we have to go over. But for now, we're just calling it 2.814. But the 814, that whole thing repeats. Kind of overdoing it with the bar here, so one nice bar there. All right, so that's really what we're looking at. That's what the mean is. Now, this information doesn't have any context to it, but yeah, like the numerical values kind of lend itself to the idea that it's not just a simple matter of taking your X values, adding them up and dividing by 5. Because what people want to do is they want to just take these numbers. I got 5 numbers there. Add them all up, divide by 5, and call it a day. Now, you might get in the right neighborhood depending on how the data is distributed, but odds are you're not going to get close enough to where you want to be in order to assure any kind of accuracy, right? And that's because this is what we call a skewed distribution. We'll talk about that more next class because the graphs are going to really kind of guide our thinking in that regard. So yeah, the idea is that a good chunk of the data is centered around 1 and also 4. That's going to impact how the calculations kind of play out, but there is room for conversation on that. Now, the median and the mode and all that stuff, that's a little bit more straightforward.
I have a question really quick.
Sure. Yeah, go for it.
I understand that the column on the left is X, but why does it say like class? Like, is that something specific that you should know, or?
That's a good question. So when we talk about frequency tables, what we do is we talk about categories and how those categories are represented. So the class, you want to think of it kind of like the class of a vehicle, like the better model, the worst model, that kind of thing, where it's simply a category, but these actually have numerical values associated with them. So sometimes we call them intervals, because if it's a range of values from one number to another, we would call it an interval. But it's considered to be a class because that is the category that it falls into. It's kind of like gasoline and how they have different octanes. You have 87, 89 or whatever, 87, 89, 91. So those are some different ways that you could represent it. It's a way of distinguishing one group from another.
Okay.
Right? Looks like there's something else in the chat here, so let me pause. So as a default, it'll say class, but it could say octane of gas. It could say time. It could say distance. It could say any number of different things. But this is your variable. All right. So the class is just how we categorize it. We're going to finish up with examples 2 and 3. And so I'll actually do number 3 first, because that's the easiest one. Because the mode, again, is the most frequently occurring value in a data set. So the mode, you want to be thinking about which number, and when I say which number, I'm giving you the choices here as 1, 2, 3, 4, and 5. Which number occurs more than any other number in the set, you know? And so when you look at that, hopefully you come up with the number 1. And that's because it has a frequency of 10. So 1 occurs 10 times. Everything else occurs less than 10 times. Right? Yeah, there's some repeated, but if I wrote out this data set, and I did, you can count up, you have some repeated values. The 2's repeated, the 4's repeated, the 5's repeated, but the 10 is repeated the most, right? So that makes that the mode, right? But as far as the median is concerned, there's 2 ways you can handle it. And one is the terrible way that I did before, and I'll just kind of flip back to that real quick. The idea that you could actually list out the raw data values and just start counting. You can say, okay, well, we got a 1 with a 5, we got a 1 with a 5, we got a 1 with a 5, a 1 with a 5, and so on. But, and I'm going to stop doing that, because that's not a good way to handle it. Because if you have a large data set, it's a non-starter. You know, if the first interval or the first class has 300 values in it, you're not going to be able to write that all out, right? So, I mean, maybe you can, but you're not going to have any, like, thinking of an assessment, you're not going to have any kind of reasonable amount of time to do that, right? So what we do is we actually use a cancellation technique, and it's actually the same cancellation technique we did for the simple raw set of data, except we're working with just the frequencies, right? So this can be a little tricky, but it's not that bad once you get the hang of it, right? So the first thing I'm going to do is I'm going to look at my values, and I'm going to say, well, I have 10 1s and 5 5s, right? Now, if I'm using the normal cancellation technique that we did on the first page, what I would say is, okay, let me find the lowest value and the highest value and cancel them out. All right, well, I have more than one highest value. I have more than one lowest value. Can I cancel all 10 of my lowest values with all of the 5 highest values? Well, yeah, but there's going to be some left over. So I can cancel some of this 10 with all of this 5. Right? So I can cancel, so we can cancel some of the 1s with all of the 5s. And the trick or the key to this whole thing is determining, all right, well, how many of those 1s? So what is that sum? Not SUM sum, but SOME. Like, how many of those 10 values can I cancel? Well, there's 5 5s, so I can cancel 5 of the 1s with those 5 5s. So that's going to leave me with 5 remaining values that are 1, right? So we always want to account for the leftover. So the 5 5s will, all of those 5s will cancel with 5 of the 10 1s. And so I can just kind of flip back real quick to this and say, instead of canceling them out one at a time, what I'm really doing is I'm taking all 5 of these 5s and wiping them out with 1, 2, 3, 4. That I can only cancel them 1 for 1. I can wipe them out with 5 of those 10 values, right? And that's going to leave me with 5 remaining values that I have not canceled yet. right? So that's the moral there, right? But then, you know, the journey isn't over. What can I do? Well, I have 5 small values, so I want to see how that's going to relate to the remaining values. So let me pause the recording. The question is this just another way of finding the median? It's not an alternative technique. It's a technique specific to frequency tables, right? So when you're working with a frequency table, so data that's organized the way that I'm showing it here, rather than just a raw list, this is the technique that you would have to use. Right? So in case anybody's wondering, it's not like, oh, let me just show you another way. It's kind of this is an important technique, right? So yeah, I have 5 1s left over. I want to cancel all 5 of those 1s with. Ideally, I'd cancel them with all of the 4s, but I can't. I can only cancel them with 5 of those 8 4s, right? So that's going to leave me with 3 4s left over, right? So we can cancel all of the remaining 1s with some of the 4s. All right, so we can cancel all of the remaining 1s, so all the leftovers, but I can't cancel them 1 for 1 with all of the 4s because I only have 5 1s, but there are 8 4s. So I can only cancel them with 5 of those 4s. All right, so I got a question coming in. Is it just subtraction, or is there more to it? No, you're really just subtracting, but I'm trying to get at the reason why you're subtracting. That's all. All right. So now I'm looking at 3 remaining 2s and 3 remaining 4s. So this is great news because what I can do now is I can wipe out all 3 of those 2s with all 3 of those 4s. So we can cancel all remaining 2s with all remaining 4s. All right, and so what that does, it leaves me with 1 value. So there's 1 remaining value. That remaining value is the 3. All right, so 1 remaining value is 3, so therefore the median is 3. Now, this is a source of aggravation for lots and lots of people. One, because it's like, you see all these words and you're like, there's got to be an easier way. Well, this is the easier way. Short of doing it on the calculator or technology, which I'll show next time. But you look at this and you say, well, isn't the 3 just the middle number between the 1 and the 5? Why do I got to do all this other crap? It's a coincidence. All right, this is it's a skewed distribution, but it's balanced by the fact that there are exactly 13 values less than the 1 and 13 values more than the 1. And because of that, that 1 corresponding to the 3 gives you the median, but it doesn't always play out that way. All right, so a couple of questions coming in the chat. So just going back to the beginning, it wasn't so much that I randomly, I'm not choosing values as much as I'm letting the data decide where I'm starting. I started with the 5 and the 10 as the frequency values, specifically because those corresponded with the lowest and highest values in the data set, right? So we're always looking at the lowest and highest values of X and what frequencies they correspond to, and then we start the cancellation process from there. Right, so that's the rationale on that. All right. There was something else I was gonna say. We got a red alert. We got a red alert. Let me pause the recording. I think I'm actually done with the recording, so I can kill that.